Hello. Now we are going to continue our discussion of synthesis of compliant mechanisms using topology optimization. We discussed in the last lecture 5 different formulations and why all of them actually behave in the same way, even though there are different formulations in literature, but there is not really much difference in the way that they behave, there are only subtle differences. In a sense, what we are after is a formulation that can give a compliant and at the same time a stiff design that will meet the functional specifications that we have. So, it is not enough to have only compliance, we should have compliance and stiffness, as I emphasized at the very beginning of this part of the lectures, that this was figured out a long time ago in the case of beams and other things, where this concept of mutual strain energy was put forth. Now, today we are going to discuss two problems that we identified in the last lecture, which is the appearance of these point flexures or what are called one node hinges. So, we have a method now that came from structural optimization applied to compliant mechanisms, where we are getting basically something that imitate rigid body linkages, because all the topologies that we get have these joints in them. So, we are essentially designing rigid body linkages, which is not a bad thing, but our original goal of getting a compliant mechanism that does not have joints is not served. So, let us analyze that today, why the joints appear and how to avoid them. So, that takes us to what we are going to call distributed compliance. So, let us look at what distributed compliance is and how to get it. So, our focus today is distributed compliance, or a tagline is point flexures and how to avoid them in optimal compliant topologies. So, let us recall that there are these different so called or seemingly different formulations, 5 of them we chose, and we showed that they give pretty much similar results in terms of designs, and all of them suffer from this problem of giving point flexures or one node hinges or elastic pairs. There are some narrow portions where most of the rotation takes place, that is a clue to what we are going to talk about, and basically they are like rigid body linkages, right. So, first let us see one more time recalling what happens. So, when we get a topology like this, all the things that we have encircled in red are basically these point flexures or one node hinges. How do these hinges occur? If you notice any one of them, we have an element and another element which are both black. Okay, I am not using black color, but basically material there, and this acts like a flexure. It is at a single point, that is why it is called point flexure with a hyphen maybe, point flexure, or they translate to elastic pairs. Okay. And we can take another example, little bit more complicated, where it is fixed at the top and bottom edge, force is applied over here and we want displacement in this direction. The algorithm for this specification gave a design like this. If we zoom in this portion which is shown here, we see really, if we zoom in, we get 2 of these solid elements connected diagonally at a corner, and that corner is our point flexure, or where it is urging us to put a hinge, put a hinge, put a hinge, put a hinge. That is what we are getting. Or if you take a portion which seems to be somewhat distributed like that, if we enlarge it, which is this one, again we have these point flexures everywhere. So, the algorithm seems to be dependent on all these point flexures in order to give maximum displacement, because we are maximizing mutual strain energy, which is nothing but displacement output point. The way to get this is to go for this point flexures, where there is rotation taking place and the bending takes place and it is able to give the displacement. If that is what we want, then there is another way to get, easier way. You start with a linkage. So, here we have a linkage and we take that linkage, and wherever the joints are, it is a 4 bar linkage. So, we have 4 joints, right. So, if you want 4 joints, that is overlaid here with dashed line in this thing here. So, we have the 4 bar linkage, right. So, there is one joint, another joint, third joint, fourth joint, this is the same body. So, it is a straight line motion mechanism, but we have that. So, if you really want to get that, you can take a sheet of material and run your milling tool along all of these in this fashion and remove all that material. What will be left out will be your mechanism with this point flexure. So, here we have point flexure, what we call elastic pair at the beginning of this course, right. So, these elastic pairs you can have it and you have the topology. But of course, in the case of linkages, we have something called type synthesis, number synthesis, that tells you what type of joints you should have and how many you should have. With all that knowledge, you can design a linkage and go to the equivalent compliant mechanism, but such a compliant mechanism, let us call that a discrete compliant mechanism, because it has basically discrete rigid bodies connected with elastic pairs, even if it is a one piece one, meaning that like this particular thing here, where we will be able to cut it out of a single sheet of material, but its compliance is limited to a few discrete locations. There are discrete number of rigid bodies and there are discrete elastic pairs joining them. So, it is basically a rigid body linkage, but it is just using elastic pairs. Why are they bad? Why are they not good enough? They are not good enough because the range of motion will be quite limited if you use these elastic pairs. They are excellent when the range of motion is limited. In fact, they are widely used in precision mechanisms, where the range of motion is not as important as avoiding backlash and friction related and wear related problems. But here in compliant mechanisms that require large range of motion to compete with rigid body linkages in terms of the things that they do, we cannot depend on only this discrete compliance, where we have a few elastic pairs connecting rigid bodies. We want something that is more distributed compliance. So, what do we mean by distributed compliance? So, again if you look at what we have, if you solve a topology optimization problem, let us say we get something like this, we immediately see that there are joints, there are 4 joints, 4 bar linkage, very often it happens. So, you can go there and then from there you can get to the flexure design again by taking a sheet of material and cutting out all this. So, we get this elastic pairs over there, over here and over here and over here, 4 of them just corresponding to what we got. But we could have gotten directly from here, okay, like synthesis that we discussed for pseudo rigid body model based method, where we can get something like this, we can get here. So, there are 2 ways to get here. So, why bother using structural optimization? All we are going to get is something that we can actually happily do from linkages. That is a question that bothered the people working in this area for quite some time, and everybody was after, or at least everybody wanted these distributed compliant mechanisms. In order to understand how to get distributed compliant mechanisms, first we need to understand why these point flexures actually occur. It is actually quite straightforward if you think about it. What are we doing? We are trying to maximize, we are maximizing MSE over SE in whatever formulation that we want. right, subject to volume constraint or not, that is a different question. This is our objective function. So, it tries to make, in order to maximize this, or we say minimize negative of that, it is the same or equivalent. When you want to maximize mutual strain energy, which is nothing but output displacement, again we are emphasizing that a lot, this is nothing but output displacement. You want the algorithm to maximize output displacement, and what is the denominator, which is SE, that is strain energy. The ratio is what you want to maximize. So, ratio you can maximize if you maximize the numerator and minimize the denominator. So, on the one hand we want to maximize the output displacement, on the other hand or at the same time we want to minimize the energy, so that the ratio will be large. Okay, now think about it. This can be achieved very easily or almost perfectly with a rigid body linkage. For a rigid body linkage, for a given force, there will be a lot of displacement, basically maximizing displacement, and strain energy in them will be 0, because there is no elastic pair, let us say rigid body linkage with kinematic pairs or kinematic joints, there is absolutely no elastic energy, there is no strain energy. So, that is actually 0. So, when you want to maximize, you can actually make it infinity, even when output displacement is finite based on the mobility of a rigid body linkage that we have taken. The denominator is close to 0, it actually can go to infinity, the objective function MSE over SE. So, that is exactly what the optimization algorithms developed for compliant mechanisms, topological algorithms, are able to achieve. They try to come up with these hinges, so that strain energy stored in them is quite small. It is not 0, because there will still be a little bit of strain energy, but it is very small. So, they are able to maximize the ratio in the process, because strain energy is very small at these hinges, you get enough displacement, you are able to also get maximum or very large output displacement. So, it is as simple as that. That why do they occur? The reason is that we are trying to ask what rigid body linkages very clearly eminently satisfy. So, what we were formulating so far is not for compliant mechanisms, but actually for rigid body linkages, because they satisfy so very well. They will have zero strain energy and a lot of displacement or finite displacement, rather large displacement. So, that is why point fluxes occur. It is actually interesting that algorithms figure this out. How do they figure it out? How are they able to get to the joints? It is all in the gradients, of course, they are able to give what we are asking. We are asking it to maximize the ratio, they are able to do it by getting these joints. And how are they actually doing it? So, one way of saying is that these algorithms, in the iterative process, we are doing finite element analysis. This finite element analysis has a loophole when it comes to this point flexures. That is, if I have one element which has complete material and another element also complete material, when these two are joined at a point, you might think that finite element analysis might have some problem. Actually, it does not have any problem, it runs happily, but rather something that is not desirable. It is a loophole in finite element analysis of continuum structures. If you were to do this, that is, when something happens like two elements are joined at the corner, you do not get any error, the algorithm gets some result, and from finite element analysis it moves on. And another reason is that if we were to take a problem where we have taken, if you notice, this is E0 and this other thing is also E0, and there is another one, so let me use a different color there, E and E, meaning what we are trying to do simulation here is for a 4 cell problem rather large, we are fixing it 4 cell problem where the material is completely filled here, completely filled, and so is here region. It is not a small cell, a rather large problem whatever one is interested in, and keep these at Young's modulus E and E0 and E0, meaning some material. Other things they are kept at a very low or varying, I must say, let us call this E, let us call this E, these two portions, and we are fixing it here in this problem. We are fixing this edge as it is shown there, this is fixed, and applying a force over here, rather we are applying a force over there. So, now if I indicate the displacement here as u and plot that u by L0, L0 let us say is this length, in fact that is what it is, L0, and the displacement of this point in this direction, let us call that u by L0 if I were to plot against E by E naught. Okay. So, the numbers may be small here, but it starts from this one is 0.01, that is it is 1% of the material. So, very little material is kept here, applying a force, how does it go? So, u by L0 we have, and then this one is 4 point, actually this is 5 into 10 power minus 3, the ratio E by E0 is 5 into 10 power minus 3, and this one seems to be 1 into 10 power minus 4, that ratio E by E0, but you can see at every point you are not getting infinite displacement, we are getting finite displacement. U by L0 at this point, as the largest value here is 25, here it is 5, 10, 15, 20. So, what we see here, even though we are going 10 power minus 4, next one is 10 power minus something, even then, even though the ratio E by E0 is so small, we are not getting infinite displacement for u, meaning that if something like this you think you apply a force, I am going to get a lot of rotation there and algorithm is going to crash because it is large displacement and ill conditioning and so forth, but nothing happens. Finite element analysis somehow happily allows, that is why we call it a loophole, so that we get finite stiffness is large stiffness, is small stiffness because displacement is a lot more compared to small change in the force here, but it does give finite stiffness and it does not crash and algorithm continues. So, we have a hinge here, that hinge now has a torsion spring. So, we can actually think that this hinge is not simply a hinge between two things here, we actually have a torsion spring. So, that is how this is. So, that is like an elastic pair. So, here we have a hinge and a torsional spring between the two things, and that is exactly what finite element analysis is being exploited here in order to give us a design that has hinges. Again we goes back to saying that our objective function is actually not entirely appropriate if you want to avoid hinge based compliant mechanisms or discrete compliant mechanisms. So, what we want is actually what we call distributed compliant mechanisms. So, how do we get that? Here is an idea, because we defined this mutual strain energy, rather it was defined in early works starting from Barnett and Shield and Prager, and then later we used them to develop compliance and stiffness formulations for compliant mechanisms. Similarly, now you have to think about distributed compliant mechanisms. Let us think of an energy, and the energy we know from failure analysis that we all learned, something called distortion energy, meaning this is the energy that distorts the material mostly due to shear, and that is what causes the failure in materials, in ductile materials. So, let us look at the distortion energy, where we subtract the isotropic component, leaving out the deviatory component of stress, that is S here. The stress strain matrix is C, and that we can call as the distortion strain energy, distortion strain energy or distortion energy density. We are using a small d here, meaning that it distortion energy per unit volume. So, we have this distortion energy. If we have this distortion energy, the idea is that when things are excessively stressed, and there is going to be shear, bending and all that, and if we minimize the distortion energy, can we get, because strain energy we already have put, we are trying to minimize strain energy, and that is going towards rigid body linkages. What about putting distortion energy? That is, we do not allow the elements to distort in terms of their shape, but they can stretch if they want to. That is what we are subtracting this component, because this is what causes the actual failure in ductile materials, right. So, we do not make compliant ways of brittle materials, although we could, and we do use silicon for example, brittle material, we have to limit our range of motion. Okay, our design should be appropriate, not for it to just break with brittle material. If you see ductile materials, then distortion energy becomes important, and this distortion energy will be there in the continuum when you are doing this, but we know in topology optimization some elements will be disappearing, some elements will be present. How do you know where to apply this? You do not want to put this distortion energy constraint, that is, it should not be more than certain value. We do not put everywhere, we want to put only those places which are the potential hinge locations. There are two ways that can occur for an element I. If I take an element I, that we have taken here an element I, that element I, we can have this one node hinges or point flexures occurring in two different ways. So, when these are empty, these are empty, or these are empty, and this is also empty, I this is also empty. So, we have a filter function. So, what we have here, this phi is actually a filter function, meaning that in your topology image there are going to be all of them at varying levels of gray between black and white, and you have to scan that not visually, but mathematically. If you use this expression, what it will tell you is this will have a large value whenever either this situation occurs or this situation occurs. That is, all these are candidates, right, this point flexures, wherever they happen this function will raise a flag, meaning that it will assume a high value. That is how this function is constructed. You have to pause that and look at it, then you will understand. The numbers are written, if this is I, the neighbors 1, 2, 3, 4, 5, 6, 7, 8 in both cases, how those values should be, because let us say we take this between I and 7th element, right. So, when the element in question is there and then we have the 7th one also there. So, we want to penalize this particular joint, and their distortion energy should not be very much. Only for those things we should apply this distortion energy constraint, that this should be less than or equal to some value that you put upper bound, so that things do not bend a whole lot. So, if you do that, we can go back to our objective function of maximizing the output displacement or minimizing negative of that, subject to this filtered distortion energy constraint. We go from 1 to n, where n is number of elements, this is number of elements, and this is the distortion energy of that element that we have discussed, distortion energy of the ith element, and then we have this filter that we just discussed, and then we have the volume constraint as usual, volume constraint. Okay. So, when you have all of this, we hope that we do get a solution, because now we are not targeting strain energy, because that strain energy will be 0, and then we go towards, or very small, we go towards rigid body linkages, but now we are trying to see that we are avoiding the distortion or limiting the distortion, so that things do not bend excessively at a few points. Of course, this is all integrated form with one value put in, but locally is what we want to get, and that is why this particular formulation still cannot completely avoid the joints. If you see, there are two things, this is with actually this is without filter, and this is with filter. In both cases, distortion energy was put as a constraint, and we do have these hinges, they do not go away. There is a slight difference. So, where there is this type of thing here, one node hinges, now they become little bit better. So, originally in this formulation without filter, when we do it, it was like this. Here what it does is, it does this. So, that is material is here and here, this is how it is here. When you actually start penalizing the points by putting this constraint, then it barely avoids it by going for this. In fact, because of this, some others in particular, Professor Anupam Saxena, IIT Kanpur, has extensively worked on what he calls hex elements. So, you discretize your structure not with square elements, but do with hexagonal elements, and each hexagon you divide into 2 quadrilaterals. So, each of these is now a finite element quadrilateral. Now, what it does is, both of them will have this and this will have the same row. Okay, let us call it rho I, and similarly this and this will be rho j, and then rho k. That means that together they exist or they disappear. Then the contact between existing elements is always via an edge and not a point, and that anyway we are getting here, an edge contact. If you put this with filter, distortion energy constraint, it does avoid things like one node, they become one edge. A little improvement, but not a great improvement. The same thing with these hexagonal elements. So, what you get here is, instead of point fluxions, you get edge fluxion, you still have a narrow one. So, like this, people have tried a number of methods, but algorithm wants to go towards this jointed designs, and that is something that we are not able to avoid, but there is a way to do this, and that is dependent on how we quantify this distributed compliance. How do we quantify what is distributed compliance? What do we need to do? We need to get a compliant mechanism. Can you tell that this is a discrete compliant mechanism? Probably it is easy, because we see that there are a few portions where the strain energy is concentrated in a discrete way. That is where most of the elastic deformation takes place. You can call it a discrete compliant mechanism. But what do you call a distributed compliant? Is it the one where elastic deformation is uniformly distributed? Yes, in words that is what it means. We have to have the elastic deformation happening throughout the structure, but how does it happen? Is it possible at all to come up with a criterion, quantitative measure that says that this mechanism is this much distributed compliant, right, as opposed to discrete? If we put some spectrum, one end is discrete, other end is distributed fully uniformly everywhere. Is that really possible to have a compliant mechanism where the stress is the same throughout? In a structure it is possible, you can do that, that is what called uniform or fully stressed design. Is that possible to do in a compliant mechanism? Because compliant mechanism, the strength or stress is not the criterion. The criterion is actually functionality. It has to move or give a motion in a particular way. If that is there, can you get uniformly distributed stress? and that is the question that is to be answered. So, we will end this lecture now and continue this point in the next lecture. Thank you.